Welcome back everyone. In this lecture we will continue with the definition of sign map. So like I promised, we will actually go through the proof of the different definition of sign map. So let us first recall what we did in the earlier class. So we introduced this delta, so which was motivated from this Vanderman matrix. So this delta is a multivariate polynomial which is given to be the product xi minus xj when 1 less than or equal to I less than j less than or equal to n. So this multiple of all these monomials. So given this n, we fix these commuting variables x1 etc xn. So using them you define this delta. So these are commuting variables. So we wanted to use this delta in order to define this sign map. So for that purpose, for given sigma coming from Sn, we define what is called the sigma of delta. So sigma of delta obtained from delta by permuting the variables xi with respect to sigma. So this is by definition you take again the product, take x sigma of I minus x sigma of j. Okay. So where 1 less than or equal to I less than j less than or equal to n. Okay. So if you think about it, so if you work with the Vanderman matrix, so basically all you do is you actually permute the columns of the Vanderman matrix with respect to the given sigma. Then if you take the determinant of that, you get exactly this polynomial. Okay. But one can actually, like I said, one doesn't need to involve determinant directly. One can work with the possible formula of the determinant and then we can define the sign map without getting into the actual determinant. But in some sense, the determinant properties are hidden in the definition of sign map. Anyway, what we have observed, so we observed that this sigma of delta is given by minus 1 power this cardinality of a sigma times delta. So where this a sigma is given to be those tuples ij coming from in cross in such that I is less than j but sigma of I is greater than sigma of j. So you collect those tuples ij such that when you apply sigma the order is changed. Okay, that is called the set of inversions that is associated with the sigma. Then the cardinality of that a sigma is involved in this sigma of delta. So it's basically sigma of delta up to a sign is exactly delta. The sign is determined by this parity of this cardinality of a sigma. So now what we want to claim, so as I promised earlier, our claim is the sign map that we already know. So that is going to be exactly minus 1 power the cardinality of the sigma. So whatever the sign that picks up by applying the sigma on delta, that is the sign you get for the sign of sigma. So that is what we want to claim. Of course, how one can prove such statement? So we can use the group homomorphism property of the sign map. So recall that the sign map is indeed group homomorphism. So in particularly what is there on the right hand side, you have to prove it is a group homomorphism. So define the following map epsilon which is from this Sn to plus or minus 1. So how it is defined? So basically epsilon of sigma is going to be plus 1 if sigma of delta is delta. It is minus 1 if sigma of delta is minus delta. So basically from our formula you can see that epsilon of sigma is nothing but the minus 1 power cardinality of a sigma. Okay. So this is your sigma. So our first aim is we need to prove, okay, we need to prove directly that epsilon is a group homomorphism. Okay. So once we prove it is a group homomorphism, so then step 2 will be, so this is going to be step 1. So step 2 will be if you verify that epsilon of any transposition ij, or even we have already proved that I plus 1, these adjacent transpositions or simple transposition, they also generate the symmetric group Sn. So, if you take this adjacent transposition I plus 1, and if you verify that epsilon of that I plus 1 is same as sine of I plus 1, which is minus 1 for all I less than or equal to n minus 1 less than or equal to 1, then these two facts together will imply that epsilon is same as sine map. Okay. So, we need to check these two facts. So, let us check one by one, and then we can actually verify epsilon is same as sine map. First of all, we will verify actually step 2, which is easy to verify. So, let us see that what this sigma equal to I plus 1 does. If you take sigma equal to I plus 1, then if you apply sigma to delta, then you can see that you just keep all the products, okay, product xr minus xs, where r is less than s, less than or equal to 1, greater than or equal to 1. Okay. So, then this the tuple rs should not be I plus 1, that is all. Okay. All these products will stay as it is, because nothing changes, because sigma only disturbs I and I plus 1. So, then you can see that it just disturbs that I plus 1 and it interchanges. So, it is going to give xi plus 1 minus xi. Okay. This is the only inversion that is possible. All other tuples stay as it is. So, then it says that from this you can easily see that. So, when you write this particular monomial in the correct order, then this is going to be minus xi plus 1, and then if you club it with this product, so then you can get just minus 1 times delta. Okay. So, that means sigma of delta is exactly equal to minus delta, but we already know that the sine of I plus 1 is just minus 1, because sine of I plus 1 just switches that ith row and j I plus 1th row, or ith column and I plus 1th column in the identity matrix. So, you get by switching that determinant, you get just minus 1. Okay. So, this we already know this part. So, now we verified these two are same. So, that means, so this is exactly implies that sigma, the sine of sigma is same as epsilon of sigma for sigma equal to I plus 1. Okay. So, that proves that step 2 is correct. So, now we need to verify that epsilon is actually indeed group homomorphism. So, for that we need to actually check how it acts on delta. So, you see it is actually easy thing to check. Suppose if you start with sigma and sigma dash from Sn, then you want to see that how sigma dash as a permutation act on delta. So, then you can easily see that. So, then as a permutation this is going to act like, so you just it is going to permute sigma dash. Okay. So, it is the composition is going to permute. So, but what it is basically it is a product x sigma composition sigma dash applied on I minus x sigma composition sigma dash applied on j, where I and j just varies from 1 to n such that I less than j. So, now what is this? Just look at this particular monomial. Okay, just write it out. So, this is x sigma dash of I minus x sigma dash of j. Okay. So, if you think about it, so this is obtained from two steps. So, first what we can do, so we can just you can start with xi minus xj, and then you can apply sigma first, then you will get x sigma of I minus x sigma of j. So, then you apply sigma dash, sorry, first you apply sigma dash So, then you apply sigma. So, then you can see that by applying like this, from 2 steps you get these polynomial. Okay. From starting with this particular monomial, first you apply sigma dash, then you apply sigma, then you get this monomial. So, that means what it says, so basically sigma dash of delta can be obtained by first apply you sigma dash to delta. So, then you apply sigma to that sigma dash of delta. But you already know that what is sigma dash of delta? Sigma dash of delta is going to be that epsilon sigma dash delta. Similarly, if you apply sigma of sigma dash of delta, then you can see that this epsilon sigma dash is constant. So, we are only permuting the variables. So, this is going to just pop out. So, then it is going to give you sigma of delta. So, then you can see that from this it is just epsilon sigma dash. So, sigma delta can be replaced by epsilon sigma delta. So, basically what it says, this says that sigma sigma dash delta is nothing but epsilon sigma dash times epsilon sigma delta. So, this is what we get. But from the definition you can see that sigma sigma dash delta is nothing but epsilon sigma sigma dash delta. Okay, combining this star and double star, from star and double star, we can see that epsilon sigma sigma dash is same as epsilon sigma times epsilon sigma dash. So, that means this epsilon is indeed group homomorphism. Okay. And this is true for all sigma sigma dash in Sn. So, that proves that this epsilon is indeed group homomorphism. So, now if you start with any sigma, then what you can do? So, for any sigma in Sn, so then you can write this sigma as some product of tau 1 etc. tau r, where this tau k, they are all coming from these simple transpositions I plus 1. Okay. So, then by looking at this epsilon sigma, you can see that this is going to be exactly epsilon tau 1 etc. epsilon tau r, which is going to be minus 1 power r. But if you apply sign map, sign of sigma is going to be again sign of tau 1 etc. sign of tau r. So, that is again going to be minus 1 power r. So, from this you can see that epsilon sigma is same as sign of sigma for all sigma in Sn. So, that means indeed the two definition of the sign map, they coincide. So, one is given by straight away determinant of this permutation matrix. So, another one is implicitly given by this delta. Again in the literature, like if you see some other books, okay, again they use some other way of defining this sign map. Again implicitly that uses the properties of determinant. Okay. For example, some of the books uses this particular let us call it xi, okay. So, which is just a product of just integers, take I minus j, where 1 less than or equal to I, less than j, less than or equal to a. Okay. Then you can apply sigma on xi by just taking product sigma of I minus sigma of j, then you vary over again I less than j, less than or equal to a. So, then if you are interested in capturing the sign, okay, you can take it as exercise. Then the sign of sigma is going to be sigma of psi divided by psi. Again you can change the order if you want, not a problem, you can actually, but anyway, so this just works. But if you think about it, again this term again can be, okay, realized as determinant of something. Okay. Again you are playing with the determinant only. Okay. So, this actually introduces sign map in many different ways. Okay, so now you can see that if you take for example this from this we can get this immediate corollary from what we have observed. So, we also have this different expression of this sign of sigma, which is given by this number of involution, which is exactly minus 1 power the cardinality of A sigma. Okay. Maybe it is actually a good exercise to do that when you take the composition of two permutations sigma sigma dash, then how this the cardinality of A sigma sigma dash related to the cardinality of A sigma and cardinality of A sigma dash. Okay. But as an immediate corollary, one can immediately get if you take cardinality of A sigma sigma dash. So, this is going to be congruent to the cardinality of A sigma plus cardinality of A sigma dash modulo 2. Okay. So, up to the multiple of 2, then they are same actually. So, this is immediate corollary because epsilon is a group homomorphism. So, this is something one can directly try to check using the definition of A sigma. I will leave it to you to check. Okay. So, now if you think about it, so if you are interested in finding out, okay, so epsilon of any transposition ij without computing, okay, this how the ij act on this capital delta. Okay. So, what one can do, one can use this property of this epsilon, it is a group homomorphism, and any transposition is all the once the cycle types are same, they are all conjugate. So, that means any two transpositions are conjugate. Using that information, you can immediately calculate this is exactly minus 1. So, how one can do, for example, you take 1 2. Okay. So, 1 2 and ij, they are both the transpositions. So, that means there will be some tau such that tau 1 2 tau inverse is going to be ij. So, this is something we have already seen. If two permutations they have same cycle type, they must be conjugate. So, any two transpositions are conjugate. In particularly, if you compute epsilon of ij, so this is going to be epsilon of tau, epsilon of 1 2 and epsilon of tau inverse. But tau is being epsilon being group homomorphism, and it is happening inside plus or minus 1, that is a commutative group. So, that means this is going to be exactly equal to epsilon of 1 2, but epsilon of 1 2 we already know it is minus 1. Okay. So, this is another way of computing, okay, what is epsilon of ij. But I urge you to just use the definition directly. Okay. So, you compute how this ij act on delta, and then you see, you try to prove it is exactly minus delta. So, this is some interesting exercise that you can do directly. Okay. So, now from this you can easily define what is called this even permutation and odd permutation. So, based on this epsilon, okay, of course, epsilon sigma is 1. So, then we call this sigma is even permutation, and epsilon sigma is minus 1. So, then we call sigma is odd permutation. So, now from this you can make a table like in the over integers. Okay. So, even times even, you can easily see that that must be even, and odd times odd, that is also going to be even. If you take odd times even, so that is going to be odd, which is again even times odd. Okay. The product of two even permutation must be even, and product of two odd permutation must be even, and if you mix this odd and even, then that must be odd always. Okay. This is something trivial to check. So, now if you take a m cycle, okay, if you take this m cycle, so let us call it sigma a1 etc. am. So, then you can see that So, this sine of this sigma, so this is going to be exactly minus 1 power m plus 1. Okay. So, because if n m equal to 2, then the sine of this a b is minus 1. Okay. That is what we have observed. When you take 3 cycle, we just observe that. So, a b c if you take, so then we wrote it as a c a b. Okay. So, then the sine of this is minus 1 square, which is plus 1. So, that means this is all lie in a n. Now, how one can check this? So, you write this sigma, this a1 etc. am as product of transposition, then it is a1 am and then a1 am minus 1 and so on, then a1 a3 and a1 a2. So, this is your cycle a1 etc. am. For example, one can check easily. So, a1 goes to a2, a2 are all fixed in this. So, that means it is just a1 goes to a2. Similarly, a2 goes to a1, a1 goes to a3 and a3 is fixed in all this. So, a2 goes to a3 and so on. Okay. So, now from this you can easily see that the sine of this a1 etc. am is going to be minus 1 power m minus 1. There are only, so it starts with 2, ends with m. So, there are m minus 1 terms. So, this is minus 1 power m minus 1, which you want to just parity wise add 2, then it will become minus 1 power m plus 1. Okay. So, that is your sine of this cycle a1 etc. So, in many places this sine map very explicitly used. For example, if you have the determinant of formula for given any n by n matrix, okay, that is the place where it is very much used. Okay. If you start with a matrix A, so which you call it Aij, which is n by n matrix. Let us say this is there in some mn over a field f. Okay. So, f is a field. For example, you can take it to be complex numbers, real numbers or even rational numbers. Okay. It is just any field. So, then we are able to do this multiplication, divisions and so on over this f. Okay. So, now we have this very explicit formula of determinant. Okay. So, the determinant can be defined in many ways. Okay. So, it is a alternating function satisfying some properties, but anyway. So, I am going to just write down very explicit formula using this sine map. Okay. So, that is all I am going to do. So, the determinant of this A is given very explicitly sum over all sigma in Sn, and then you take this sine of sigma. So, then you take this product of A1 sigma 1 and so on A n sigma n. Okay. So, this is the formula for determinant using the symmetric group action and the sine map. So, what is this, how this sigma act on this Aij? You can see that it naturally act on this integers 1 to n. So, you basically take the corresponding numbers here, okay, a1 sigma 1 and so on a n sigma f n. When sigma is identity, then you get exactly the diagonal product. Okay. When sigma is non-identity, you can already see that. So, there will be some tuple ij such that I not equal to j. Okay. For example, let us write down this for n equal to 3. So, you can try to verify this is the formula that you must have seen in your high school. Okay. The determinant of this A. So, when A is just A11, A12, A13, A22, A21, A21, A22, A23, A31, A32, A33. So, then the determinant is given by, So how many terms you have in S3? So S3, the cardinality is 3 factorial, it is exactly 6. Okay. So you can write down S3 very explicitly. So this is going to be identity and then the transposition 1 3 1 2 1 3 and 2 3. So 3 transpositions are there. So then you have the product of them. So you will have the 3 cycle 1 2 3 and then I guess it's 1 3 1 3 2. Okay. So let's check. So if you take the product 1 2 1 3, so that is going to be, so 1 2 3, so 1 goes to 3, 3 goes to 3, 2 goes to 2, 2 goes to 1, so 3 goes to 1, 1 goes to 2. So this is exactly 1 3 2. Okay, so this is the product, so which is equal to this. Similarly, if you take 1 2 2 3, so this is going to be 1 2 3. So let's check. So this is 1 2 3. So 2 goes to 3, 3 goes to 3, 3 goes to, sorry, 1 goes to 1, 1 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 3, 3 goes to 2, 2 goes to 1. So this is going to be 1 2 3. Okay. So these are all the 6 terms. So it's clearly all the 6 terms. So then you can see that you can write down. So the sign will be what? The sign will be, so this is going to be plus and this is minus, this is minus, this is minus and this is plus and this is plus. So there are 3 plus terms and 3 minus terms. So then if you write it down, so for the identity it will be A11, A22, A33 and then minus. So now you have to see where this 1 2 does. So it is A1 sigma of 1 is 2, A12 and then A2 sigma of 2 is 1, A21 and then A3 sigma of 3 is 3. Then minus. So you can see that A1, so this 1 goes to 3 and then A2, 2 goes to 2 and then A3, 3 goes to 1. Then minus A1 goes to 1, A2, 2 goes to 3, A3 goes to 2. And then plus similarly, so 1 2 3. Okay, so A1 goes to 2, A2 goes to 3 and then A3 goes to 1 plus A1 1 goes to 3, A2 2 goes to 1, A3 3 goes to 2. So these are the terms. So you can cross check. Okay. So this is what you get using this standard formula for the determinant. For example, you can cross check like this. Okay. This is A11, A12, A13 and then A21, A22, A23 and then A31, A32, A33. So when you take determinant of this, then you have this expansion using cofactors, then you get this exactly. So you put plus minus plus here. So this is A11, then A22 times A33 minus A32 A23. Okay. Then minus A12. So you cross this, then you A21 A33 minus A23 A31, then plus A13 and then you can see that this is A2, sorry, you have to cross this. So A21 A32 minus A22 A31. So let us check only 1 or 2 terms. So it's clear that the very first term, that is A11, A22, A33, it is there. So that is this term. And then let's check the second term. So A11, A32, A23. So A11, A32, A23. So this is this second term, 2, 3, 3, 2. Okay, with the minus sign. So, that is matching. Similarly, you can see that A122133, A122133 with the minus term. So, this is here A122223. So, this is there, and now let us take 122331, 122331 with the plus sign. Okay, so that is also matching. So now I will leave it you to check. This also appears as the extra term. So this actually kind of gives very explicit formula, okay, for the determinant using the symmetric group action on the AIJs and with the sign map. So this is I would say very first instance that you see the power of, okay, the sign map as well as the action of Sn on the indices, okay. So and one can get such useful formulas very explicitly. Okay, so I will stop here and then we will continue with some automorphism of groups in the next class. Thank you. I will stop here.